Assalamu alaikum dear students, we're back with another video lesson. In today's video lesson, we're going to start with chapter number 4, and that is about sound here. We've kind of learned about sound a little, but we're going to learn more details about sound and also some other concepts that are related about sound as well. So what are we going to learn in this chapter? The first thing that we're going to study is sound waves, Basha, and then after that we'll talk about sound intensity and resonance, and then the last thing is going to be harmonics, Basha, which is sort of related to the sounding waves that you studied in chapter 3, section 4. Basha, so what are sounds here? The first thing we're going to learn about is sound waves, and also we're going to talk about the production of sound waves as well, Basha. All right, so what are sounds in general? We've learned that sound waves are longitudinal wave, yes or no? So, and also in order to travel, they need a medium, right? So that is two things. And also in order to produce sound, there must be a vibration. So we can say every sound that is made by a vibration. That is the first thing you need to know. The second thing is sound waves are longitudinal. Why are longitudinal? Because as the sound wave travel, it makes the particle of a medium to vibrate parallel to the direction of wave travel. And because the particles are vibrating parallel to the direction of wave travel, we call that kind of waves longitudinal waves. So what exactly a sound wave is? We said that it is a longitudinal wave. How does it transmit energy? It transmits energy through a medium by making the particles of a medium to vibrate. But what kind of vibration? Parallel vibration to the direction of wave travel, Basha. So now consider we have a tuning fork, Basha. You've learned about tuning fork, or perhaps you've seen a tuning fork before. So here's a tuning fork, Basha. These parts of a tuning fork, we call them prongs in here, Basha. So this is a tuning fork, and this is prong. So what happens when you struck a tuning fork, Basha? Once you struck a tuning fork, it is going to vibrate back and forth, Basha. So once it is vibrating, let's say forward in here, this is how it is going to be, right? The tuning fork, it is coming forward, yes? But as it is coming forward, it is going to push all the air particles closer to one another. So it is, as it is moving or pushing the air particles closer to one another, it forms a region of what? A region of, what do we call this region? Region where the pressure and density is maximum, and we call this region rarefaction. But what happened as, for example, the particle, or as the prong, let's say, moving backward here? As it is moving backward now, so because these sound waves are traveling, so let's just move this one forward a little here. So this is what happened here. But what happened as the prong is moving or vibrating backward here? It forms or produces a region where there is less air particle, Basha. This less air particle, what do we call this region? We call this region rarefaction. So now these regions are going to continue or repeat here, and this is what is going to be called a sound wave here. And why is it called longitudinal? We'll talk about that one too in a second. But how about if we just flip this one here? Actually, it makes no difference here. Okay, so we'll start with rarefaction first. Normally, you might see longitudinal first, but at this point, I guess we'll just start with the rarefaction region first. It makes no difference, Basha. All right, so let's just erase this tree here because these are something we really don't want. All right, so now, once again, as the tuning fork vibrates, this is the shape of the air particles that you would normally notice if you could see the air particles, Basha. But this is how, the particles would be in reality. Once again, now, if you notice, we have two regions. We have a region where we have maximum pressure and density, or the air particles are very close to one another. What do we call this region? We call this region compression. Basha, compression. What about this region here, or this one? Doesn't matter which one, right? You choose here. This region, there is less air particle here, so we call this region rarefaction. What do we call this one? Rarefaction. Now, we also know that, so it repeats as you can see here. We also can see that in compression, these air particles are closest to one another. So at this point, there is maximum pressure and, of course, maximum density as well. So let's say at this point here, we have maximum pressure and density, Basha. So we can say at compression, we have maximum what? Maximum pressure and density. What about a refraction? It's going to be exactly opposite, right? So it is going to be minimum, right? Minimum what? Minimum pressure and density. Density. This is how you can produce a sound using a tuning fork. Once again, without striking the tuning fork, without the tuning fork vibrating, there will be no sound at all in here. Okay, now this is what happens once we strike a tuning fork, and this is the thing or the shape of the sound particles that you see. Now, these particles, or we can say this is how the wave is traveling. So let's perhaps bring this one here. So this is how the sound is traveling. If we take one particle as an example here, how do you think the particle is vibrating here? So we can say a particle, or if we take a particle here, this particle will be vibrating back and forth, only back and forth. But what is traveling? It is, we can say that it is the energy of a sound will be traveling or passing through the medium here. Okay, now that'll be regarding this, Basha. What else do we have? There is one more thing here. Now this sound wave can be represented as, which is a longitudinal wave, can be represented as a sine wave here. Now previously we've mentioned that, right? So let's see if we can move all this down so that we could draw some sine wave here. Okay, so if I want to represent this wave as a sine wave, how would I do that? And if you remember, I'll just start at this point right here, Basha. So starting here, good man, the center of every compression represents or corresponds to crest, Basha. And the center of every refraction would represent what? Or corresponds to a trough in here. So you can see the center of every compression corresponds to a crest. The center of every refraction corresponds to a trough, and then you can see that this continues as the wave passes here. But remember, if we're going to draw this or say this is a sine wave, then at this point here we have pressure, or there must be written pressure or density, or you can write them both here actually. Okay, so if it is going upward, that would be maximum upward. If it is going downward, it is going to be minimum pressure and density here, because this wave it is, you can see that we have different regions, Basha. So low steady would be maximum pressure and density. If it is, for example, moving downward, which is representing a refraction, there is minimum pressure and density right here. Now we have a question that says, why are sound waves characterized as a longitudinal wave? Well, for one of the reasons, because sound waves, in order to begin with, it needs to be a particle that it can vibrate, or something that vibrates, Basha. So we can say it is caused by vibration one, yeah? So it needs something to vibrate first, and then this vibration must be transmitted. So if there's no particle to vibrate, will there ever be a sound in the first place? No. Now, after the sound is made, it needs particle to continue or to move, to transmit through the medium. If without a particle, it cannot travel through, Basha. That is one of the questions that we had. There is another question that says, why? That'd be one of the questions we have now. You'll see that it says, why sound waves are characterized as longitudinal? Well, because sound waves make the particle, Basha, or the particles of a medium to vibrate parallel to the direction of wave travel. This is why we call this one, we call sound waves longitudinal. But there's one thing I need to tell you here. Once it comes to drawing these sine waves for a longitudinal wave, but listen here. Now we know that as the sound travels through the medium here, part of this sound wave, Basha, as the sound travels through a medium, of course, the energy of a sound will be, like spread through the medium here. So, and we've also learned that the relation between amplitude and energy, right? So we said energy, it is directly proportional to the amplitude squared. Because the energy of this sound, of course, it is going to spread through the medium here. So the amplitude of a sound that it is traveling here, it is going to become less and less and less in here. So this is how it normally looks like in reality. And this effect here, we call this one damping, because the amplitude of the vibration gets less and less until it, for example, it reaches zero here. Okay, or whatever, you can see that it decreases here. But you might wonder, all the waves, for example, why all the waves that we draw, the amplitude is always the same? So for example, the waves that we normally draw, this is how it looks like, right? So this is what it looks like. And as you can see here, the amplitude doesn't change. But this is an idealized wave, you can say, or an idealized case. We assume that at this point here, no energy is wasted or lost. So this is how the amplitude always stays or remains constant. Again, now in reality, in the real world, this is how it looks like. And this effect we can call this one damping here, Basha. Damping. Now what that is, for your information if you want to know. All right, one more time. Let's go through the definition of sound wave again. Good mind, it is a longitudinal wave that transmits sound energy through a medium by making the particles of a medium to vibrate. Every sound waves are caused by vibration here. And this is the tuning fork that I was telling you about. Once you're making, for example, strike the prongs or this tuning fork, now you can see there is a little faint vibration here. You can see that. That is when the tuning fork vibrate, Basha. So now you can see here as well, once this tuning fork is vibrating, Baba, now you can see that here, as it vibrates forward, it pushes the air particle, for example, forward, it pushes the air particle closer, as you can see here. Now, once the air particles are pushed closer to one another, or compressed, it forms a region, which we call it compression one, yeah? Where there's maximum pressure and density. What happened as it is moving backward in here, which you can see here, now it forms a region where there's less air particle now, and this less air particle region, you can call that rarefaction, where the pressure and density are minimum here. Basha, we've learned about compression and rarefaction, so what are their definition exactly? Good man, first let's start with compression. It is a region in a sound wave, or you can say in a longitudinal wave, let's say sound wave, Basha, where pressure and maximum are, where pressure and density are maximum, Basha. What about rarefaction? It is a region in a sound wave where pressure and density are minimum, Basha. Don't forget that. A region in a longitudinal wave, or sound wave more specifically, if we want to start with sound, which the density and pressure are at minimum. Sound wave is a longitudinal. Remember what I was just telling you regarding this? Why are sound waves are characterized as longitudinal? Good man, because the sound waves make the particle of a medium to vibrate. But how vibrate? Parallel to the direction of wave travel. If the wave is traveling to the right, the particles of the medium are going to vibrate back and forth, which is parallel to the direction of wave travel. That is why we call sound waves longitudinal. Basha. And this is also another example of a tuning fork, Basha. So once we draw the wave, Baba, this purple part, it means maximum pressure and density. The white part means less air particle, so rarefaction, Basha. Compression, rarefaction, compression, rarefaction. We said that the center of every compression corresponds to a crest, but we cannot call a crest corresponds to. And it's almost like in the place of a crest, otherwise it is not a crest. And then this one, it is in a place of trough, and it continue like that. And we have a question here. That's the second question of chapter V. Says what? Draw a sine wave, Basha, that corresponds to the sound wave depicted below. What does depicted below means, Baba? Depicted yani shown below, Basha. Shown below. So now if this is the sound wave, you can see that this is the darkest part, so that would be a compression, rarefaction, compression, rarefaction, and then another compression, and continue. So if we start with this one here, you could start something like this here. So we want to be a little bit more precise. This is something like this one here. So this is how it looks like, Basha. Oops, no. I think because of the arrows, it just messed it up. All right, that is one. Let's just draw 3 arrows so that I don't get confused in here. Basha, this is what it is. So compression, that'll be corresponding to crest, rarefaction, that is corresponding to a trough, and then another crest, another trough, and then these are not crest and trough, these are corresponding to crest and trough. So make sure you know that. And this will be, for example, one of the best. If you start from this one here, of course, even this part, that'll be starting from a rarefaction. You can see that here. So this would be the answer to this question right here. Okay, the next thing that we have is, we can say the characteristics of sound waves here. Because we're talking about sounds, Basha. There are different types of sounds. And there are sounds that we hear, and there are other sounds that we don't hear. But just because, like, just because there is a sound that we don't hear, all right, that doesn't mean we cannot call it a sound. It is still considered a sound, Basha. What do I mean by that? Because we have 3 types of sound, Basha. Remember this. How many types of sound? 3 types. We can say types of what? Types of sound. Basha. Now, the first type of sound that we have, Baba, all right, we can go by the order here. The first type of sound we can say infrasonic sound. Infrasonic sound. All right? These are sound waves that cannot be heard by human. All right? Once again, infrasonic sounds, These are sounds that cannot be heard by human and have frequencies, Basha, where the frequency of infrasound, let's say infrasonic sounds, their frequency are below 20 hertz, Basha. These are infrasonic sound. There's another type of sound that there is, it's called audible sound. What is it called? That'll be the second type of sound. We call them audible. Audible what? Audible sound here. These are heard by human, Basha, and their frequencies range between 20 to 20,000 hertz, Basha. This is audible sound. And there's the third type of sound, which is called ultrasonic sound, Basha. Ultrasonic sound. And this sound here, again, it is not heard by humans, Basha. Their frequencies are, we can say, above 20,000 hertz, Basha. Above 20,000 hertz, we can say. So these are the three types of sound, and these are very important. You need to know them. It's been in Wazari so many times as well. Basha, we'll repeat this again. How many types of sounds are there? There are three types. There's infrasonic, there is audible sound. Audible, it's the sound that is audible, hearable, that humans can hear, Basha. And then there is ultrasonic sound as well. Basha Gutman, infrasonic, these are sounds with frequencies that are below 20 hertz. Audible sounds, the one that we hear, their frequency range between 20 hertz to 20,000 hertz. Sometimes instead of 20,000, we might just write 20 kilohertz as well. Kilo stands for 1,000, so that is going to be exactly the same as this one right here. Okay, what about ultrasonic? These are sounds that are, or with frequencies that are above 20,000 hertz, and we as humans, we don't hear them. Basha, these infrasonic, it's true that we don't hear them, but it can be heard by some animals, like elephant, for example, and these are by human. What about ultrasonic? It can be, again, it's not we as human, we don't hear them, but it can be heard by some animals, like we can say dogs, bats, and then horses too, I guess. Bats use this ultrasonic sound for echolocation. What is echolocation? Finding the location using echo. So echolocation, using location or using echo to find the location. Sometimes they do that for finding their prey as well, Basha. So it could be using for whatever the purpose they want to. So these are the sound. But remember this, previously we've mentioned about something before. If you remember, we were talking about speed. Gutman speed that says speed of a wave that the frequency times wavelength. Now, how are we going to use, or this might help us in here? Watch this. If I compare the frequency of each one of these, we can see that the frequency of infra, and you can write this for yourself as well, it is less than the frequency of the audible, Basha, of the audible, Basha. And the frequency of audible, it is less than the frequency of what? The frequency of ultra, Basha, ultrasonic. But we know that frequency and wavelength are inversely proportional, yes or no? If the frequency of the infra is the least or the lowest, Basha, what can we say about the wavelength? Basha, so the wavelength of this one, so this is the least one, yeah? Kata, the frequency of this one has to be the longest, Basha. Well, these high and low for frequency, this is the lowest, and short and long for wavelength. Kata, the wavelength of the infra, it is the longest, or you can say it is longer than the wavelength of infra, it is the longest, which is longer than the wavelength of audible, Basha, which is the wavelength of audible, it is larger than the wavelength of what? Of ultrasonic sound as well. But what about the speed or their speed here, Baba? Because, like these are, obviously, these are in the same medium, so the speed of each one of these are going to be what? Are going to be exactly the same. And this been in Wazari. Or if this question ever came in Wazari, you can always write this map, which is very easy. Of course, it guarantees that you're not going to lose 2 marks in here, Basha. It might take about 30 seconds here, and you can write it way smaller. If you want to do that, you can just write the initials here, infra, audible, Basha. Then you could make something like this, and this is ultra, Basha. Gutman, start with their frequencies, right? And you can write the wavelength as well. And then, but the speed of each one of these, Gutman, is going to be the same. Frequency of which frequency is the largest, Gutman? E? ultrasound is bigger than audible, which is bigger than infrared, yeah? But wavelength is opposite or inverse. So it is going to be, this is the longest, which is going to be longer than this, and this is longer than that, but their speed is the same. Hamzare, write this key, for example, that allows you or helps you to answer the questions pretty quickly without making any mistakes as well. Basha, this is regarding the sounds, Basha. Okay. By the way, there is one thing you need to know. For the audible, it is true that the range of the frequency that we hear is between 20 to 20,000, but this range, of course, will change by the age or once we age, Basha. Okay, so once again, audible, these are sound waves that are heard by the average human ear, can have frequencies between what? Between 20 to 20,000. Why do we say average? Because, Baba, listen, there are some, like, let's say animals, not animals. There are some humans, or some exception, Babylon, let's say in this range. There are some humans that can hear frequencies, for example, that could be not exactly this between 20 to 20 hertz. So we always say that is by an average human ear, Basha. And we also said that this, remember, this range for an adult, or the older we grow or get, this range becomes less and less, Basha. But for average human, that'll be the range, Basha. What about infrasonic waves, Gutman? These are sound waves with frequencies that are less than 20, Basha. We cannot hear them, but of course elephants can make and hear this infrasonic wave too. Okay, what about ultrasonic wave? These are some sound waves with frequencies that are more than or higher than 20 hertz, Basha. Once again, we cannot hear them, but some animals like dogs and horses can use them. We said also a bat can use that for echolocation too. And also, if you ever went to a doctor, for example, checking if you have kidney stones, they normally use ultrasonic just to check if you have kidney or not. Sometimes mothers go to do, for example, this just to check if the baby or the fetus is all right, Basha. So these are the kind of waves. Sometimes we just call this one sonar, Basha, but in reality it is the ultrasonic waves there. And this is the key, for example. You can write it down and then before answering any question that is related to that. Basha, now we have another question. What does it say? It says, what are the differences between infrasonic, audible, and ultrasound? Now these are ultrasonic. These are very simple. We said audible. If we start with audible first, their frequency range between 20 to 20,000. Infra, their frequency is below 20,000. Below 20 hertz, and then ultrasonic, their frequencies are higher than 20,000 hertz, Basha. Only audible can be heard by humans, Basha. There was a study tip, or two actually, it says an individual's hearing depends on a variety of factors, including, Basha, Gutman, their age and also exposure to loud sounds here. If we said the older you get, of course, this range for you shrinks more and more, so the frequency you hear, or the range of the frequency that you hear, is going to be less and less. And also the exposure or experiences with loud noises as well. Because if you're, a construction worker or somebody else who's doing that, once they experience too much, or if they are exposed to a lot of loud sounds or noises, then of course that could affect their hearing ability and they might not hear as much, Basha. And then the next thing that we have, all types of sound waves, whether if it is audible, infrasonic, or ultrasonic, all of them, these are longitudinal wave. And once we say longitudinal, that means they need a medium to travel through. Without particles, none of them can travel through, Basha. All right, they can travel through empty space. Now here we have this question here, says, why do ultrasound waves produce images of objects inside the body more effectively than the audible sound waves do? And by the way, there was a part actually in this book was talking about the ultrasound and how it works, but that part is skipped, so not for you here, but this question is still remaining there, so the question is required from you. So going back to this, why do ultrasounds produce images of higher resolution and images that are more clear than any other waves, Babylon? The answer to that question is because we can say ultrasonic waves have a very high frequency, Basha, which means that their wavelength are pretty short. because these two are inversely proportional. And we know that if there is a lot of or higher frequency, that means the energy of that wave, of course, is a lot. So the higher the frequency, the more the energy, they can penetrate through different layers of body tissue, Basha. There is a skin, for example, there is a, like different tissues and organs. So because they have a lot of frequency and energy, so these are related, right? So it can penetrate through different layers of body tissues, and then every Babylon layer they penetrate, part of that wave will be reflected. Now that reflection will be going back to the receiver, then sent back to the computer, and then now this computer will form a image based on the frequency that got reflected or the wave that got reflected. So this is how these ultrasonic waves produce images that are better in resolution and much more clear. There's another question. Well, actually, what would happen if we were using audible sound waves instead of ultra? Well, one effect or one flaw of that would be if you, for example, going to the doctor just to check, let's say, whether you have a kidney tissue. By the way, it's called a radiologist, Basha, the person who's doing this, right? Just to check if you have a kidney stone or not, right? And then if it is using audible sound waves, then if you're talking to the doctor, maybe your sound waves will be mixed with the sound of bubbling of the transmitter. In that case, of course, these two waves might combine together or gives you a false information or a false image or data, whatever. So that would be not really safe. And also it cannot penetrate too deep because it doesn't have that much energy. All right, so we can say, once again, why do ultrasounds are better? Because they have shorter wavelength, because they have a lot of frequency, so allowing them to penetrate tissues more effectively, Basha, and then provide higher resolution or clear images. All right, and you can also say that, Baba, the longer the wavelength, they can bend through objects instead of penetrating through them, and that does not produce good images. Now we have a few Uzadi questions, actually several. Let's answer some, and then after that we'll just move forward. It says a region of a longitudinal in which the density and pressure are minimum. Always find a keyword here, Baba. Longitudinal wave, Basha. It says density and pressure are minimum. Basha Bitman, we have maximum pressure and minimum pressure. When you have maximum pressure, we call that rarefaction. Basha, what if it is minimum pressure and density? We call that actually, I said the opposite. We call that compression one, yeah? So if it is minimum pressure and density, we call that one rarefaction. Basha, can we call that pitch? No. So this is a rarefaction. Antinode, compression, these are incorrect. A region of a longitudinal wave in which the pressure is a maximum. All right? Once again, longitudinal, pressure is maximum. We call that what? Compression. Basha? By the way, we cannot say crust and trough because these are for transverse. But now you have these two, or you're left with these two, so 50-50. Yeah? Basha, 3 says what? The frequency of a sound wave heard by an average human, Basha. What is the frequency of the sound wave that is heard by average human, Basha? 120 to 200, no. 100 to 10,000, no. 20 hertz to 20,000, yes. 30 to 30,000, that is incorrect. So that is C right here. Okay, now this is the question, or the kind of question that I was warning you about, or what to do exactly. It says, which of the following is not true, Agad Levi, right? For audible, infrasonic, and ultrasonic waves in the same medium. When it says the same medium, that means the speed is going to be the same, Basha. So how about we draw the key again? Right, good man. Infra, Basha, audible, and then there is ultra. Good man. Let's write their frequencies and wavelength, Basha. My frequency of ultra, it is the largest, Basha. So this is how it goes. Wavelength, Basha, if the frequency of this one is the least, the wavelength of this one is going to be the largest, Basha. So what does the first option says? It says the wavelength of ultrasonic, it is larger than audible. The frequency or the wavelength of ultrasonic, Basha, it is larger than audible. Is the wavelength of ultrasonic, is the wavelength that is larger than audible? That is incorrect, Basha. So this is incorrect, but keep that in mind. The next one says, right, it says the wavelength of infrasonic, it is larger than audible. The wavelength of infrasonic, it is larger than audible. That is correct. Right, the next one here says the wavelength of ultrasonic, it is smaller than infrasonic. The wavelength of ultrasonic, it is smaller than infrasonic. ultrasonic. That is also correct, Basha. What about the last one? The speed of all these speeds are equal. That is also true. Should have done this one too here to complete this one. So that is obvious. So now what is the only one that is incorrect? That is option A. See how this map makes it easier, for example, it would be less confusing too. All right, then if you know or you don't need this key, that is also totally fine. The frequencies of infrasonic waves have what? With mandala infrasonic, it is less than 20. What about the frequency of ultrasonic waves? Ultrasonic now, ultra, Basha, that is going to be more than 20,000. Which one is more than 20,000? Says lies between this and this? No. All right, more than 20,000, that'll be A for this one here. 7 says the sound waves with frequencies greater than 20K. So this 20K stands for 20 kilo. Let's write this one. Basha. It says if it says greater than 20 kilohertz, kilo it means 1,000 hertz, Basha. Now, frequencies greater than 20,000 and cannot be heard by human ear. What is it called? That is called ultrasonic waves. All right, now these two are important and you need to know or focus a little. It says, which of the following waves are longitudinal waves, Basha? Which of the following are longitudinal here? So, infrasonic wave, is it longitudinal? Yes, right? Because they need a medium to travel through. What about ultrasonic? These are all sound waves, right? Audible waves, yes. So these are, all of them are longitudinal waves here. What about the next one? It says, which of the following waves is a longitudinal wave, Basha? So, an X-ray, is this a longitudinal wave? No, this is electromagnetic wave. What about ultraviolet wave? Ultraviolet wave, it is a visible light color, you can say, or color. That is, again, electromagnetic wave. That is not a longitudinal, Basha. These are transverse. What about sound? Yes, it is a longitudinal wave. The last one here says infrared wave. Again, this is electromagnetic wave that is not longitudinal. So the only longitudinal wave is a sound wave. Instead of sound wave, sometimes next time they might give you infrasonic, audible, or ultra, right? So just to confuse you, so make sure you know what are the type of sounds so that you can make the right judgment and choose the right thing here. Now, frequency determines pitch, Basha. What exactly is this? And what is exactly pitch, first of all, or to begin with? But look, there is frequency. Let me perhaps start with an example, right? Now, you're standing here or you're just walking by the, like on the sidewalk, Basha, and then you hear the sound of the ambulance, Basha, or the siren of an ambulance, Basha, and then the sound as it is approaching here, what exactly happens or how do you hear the sound? For example, the sound of the ambulance, or more likely, let's say the frequency, it is getting increased, increases more and more until it gets, or, comes close to you. Then after it passes you, then the sound, of course, it decreases as it is moving away. So you can even tell if it is getting closer or away even without looking, just by noticing or hearing the sound here. So what exactly happens as the ambulance approaches? The frequency of the ambulance that is getting to you, for example, or that you receive, that you hear, it is increasing, Basha. That frequency increase, all right, because it is approaching. But as it is moving away, the frequency decreases, so you can notice the difference between the two, Basha. But the frequency that the ambulance makes or produces or emits never change. It is only the frequency that you hear will change. And that frequency that you hear, that is what is called a pitch. Basha, Kata, what is pitch, Baba? We can say pitch, it is the perceived loudness of a sound. Basha, it is the, we can say it's a measure of, or the perceived, we can say it is a measure of how high or low the sound is perceived. It is a measure of how high the frequency or how low the frequency that you hear, that is called pitch. And that pitch, of course, depends on the frequency of the source. Basha, I got it. All right, so once again, we can say pitch. It is a measure of how high or low a sound is perceived, it is received, it is observed, it is heard. These are all keywords for this, depending on the frequency of the source. Basha, and we also have this question, which you already need to know. It's been a Wizari as well. It says the pitch of a sound depends on what, Baba? It depends on 3 factors. It depends on the frequency of the source, right? It is proportional, but we cannot say direct because the relation is not direct. right? Just like, for example, if you remember in a pendulum, it means if we double the length, will the period double? No, it will increase by the square root of 2. Here, if we increase the frequency of the source, the pitch will also increase. But we cannot say direct, because if you double the frequency, the pitch must be double, which we don't know the relation here, and it is, in fact, it is not directly proportional, but it's not mentioned in our book, like how is the relation. The book mentions just it is proportional. If the frequency increase, the pitch increase, then that is the only thing you're required to know, nothing more than that. Okay, so we can say the frequency of the source, if the frequency increase, the pitch increase too, Basha. We can say it is proportional. But how much increase, we don't care and we don't need to know. This another factor that affects the pitch is, we can say, the background noise, Basha. How would that affect the pitch? Again, you don't need to know. You just need to count or know these things affect the pitch. And then the next thing that is, we can say it is the loudness, Basha. So these three factors affect the pitch or the frequency that we receive or perceive, and then that is what is called the pitch. Pitch increases by increasing the frequency of the sound. I got that, baby. All right, now the next thing that we have a question says, what is the difference between frequency and pitch? We've learned that before. Frequency, we can say it is the number of vibrations per unit time. So, like, for example, how many times something vibrates in 1 second, that is called frequency, right? Or once you're given a number of vibration in a certain time, you just divide, you get the frequency, Basha. But what about a pitch? We said pitch is a measure of how high or low the sound is perceived or received by the observer, Basha. So this will be the difference between the two. And also remember this, we can say pitch, it is subjective. What do you mean by the subjective, Baba? That means it is different from one person to another. If we're standing, for example, right next to one another, the frequency that you hear might be different from the one that I hear. Why? Because, like, maybe you have a better hearing system or whatever, right? So it is subjective, Basha. But as al-Muhim, we have frequency and pitch. Frequency, the number of vibrations per unit time, while pitch, it is how high or low the sound is perceived to be. I guess this will be the end of our session. Inshallah, next time we're going to start from the speed of sound wave in different mediums. Till then, keep practicing, and I'll see you soon. Inshallah. Assalamu alaikum wa rahmatullah.